All right, so this is our presentation for Chapter 12, the rates and mechanics of chemical reactions. This is part of our Module 2. This is the first chapter of Module 2. So let's look at a few key points from this chapter for our second test. So we'll touch on a little bit of chemical equilibrium, which is sort of the overarching topic for the next several modules of this course and several chapters. But before we really get into that, we'll need to set the background of chemical kinetics. We'll be talking about rate laws, rate mechanisms, reaction orders. We'll talk about each of the orders in sequence here. We'll talk about collision theory, Arrhenius equation, and finally end up with catalysis. And then a little bit on enzymes as a bonus at the end. So here are some points not to focus on for the test coming from this module. Formal approaches for finding the rate laws. You won't need to delve into, a lot of the details of how these rate laws were ultimately derived, the calculus behind it. It's not going to be necessary. We're going to give all that to you. If you've had a calculus course, that may give you some deeper understanding of where these rate laws come from, but otherwise it's not necessary. I won't have any questions where you've got to count the spheres or shapes or little molecules in a set. There'll be a little bit of homework that looks a little bit like that, but I'm not going to have any problems like this. I find sometimes it makes things a little more difficult than they need to be. Drawing or reading graphical methods for finding rate constants and other parameters. I'll show you the equations and you'll use those to develop everything. Know that these methods exist, but you won't be tested on them. Radioactive decay, we've already covered that in a previous chapter, and also the list of heterogeneous catalysts that they give at the end of the chapter. You won't need to know that either. Some key terms. So chemical equilibrium. This is the state reached when the concentrations of reactants and products remain constant over time. This will be discussed more so in Chapter 13, but the underpinnings that will be needed to fully understand this will be covered in this chapter. This chapter is really going to be more about chemical kinetics, the area of chemistry concerned with reaction rates and the sequence of steps by which reactions occur. And the rate laws, the equations that describe the dependence of the reaction rate on the concentrations of each reactant in the equation. Rate laws are typically first, second, or zeroth order, and we'll talk more about what that ultimately means. And the rate constant gives us some proportionality constant that will also show up in our rate law equations. So first order reactions, as we run into those, will be one that depends only on a single reactant at one time, or to the first power. Second order to the second power, or two different reactants. And a zeroth order reaction is one whose rate is constant and independent of the concentration of the reactants. We'll also study reaction mechanisms, the sequence of reaction steps that describe a pathway from the reactions to products. So like we'll break down a reaction into the sequence of steps that physically occur, or at least theoretically physically occur. Collision theory, we'll talk about how most reactions are driven by collisions and how that statement, that understanding allows us to develop a number of theories about that, including the Arrhenius equation and other possible ways of formulating that. Catalysis also, we'll study that and how it can change the reaction rate without it being consumed in the process. And we'll see a little connection to enzymes. So that'll be close to the end of this chapter's coverage. So let's talk a little bit about rates of chemical reactions, right? Some chemical reactions are very fast and near instantaneous. We don't even really perceive them as they happen. And some are very, very slow. Like, some reactions can take geologic time scales to happen. So we're looking for ways to quantify that. How can we understand the rate of a reaction? So we can think about it as the concentration change with some time. Whether we want to measure the reactant or the product, we can look at the concentration change with some unit of time to give us a rate. It's kind of like a speed, right? It's some distance change with some time change, okay? But it's like the speed of the reaction. How often, we're going to get more of it. And there's different ways to measure that, and that's what we'll look into, right? So here they look at the thermal decomposition of some gaseous dinitrogen pentoxide. So it's going to change. It goes from some colorless gas into some brown and another colorless gas. And so this gives us maybe a way to measure it. We could measure this brown gas as it develops with a spectrometer or something like that. But if we could measure these concentration changes with time, we could plot this, right? We could use this to see the slopes and the changes in time, and we could look at the concentration at one time, subtracting some earlier time, and develop some rate of formation, right? And we could do this by picking two times in here And we could use this to get a rate. Now, some rates are constant, and some rates are not. It's gonna change, right? Some of these reactions, right, they're not just going to be linear. They're going to be curved in some way. There's going to be curvature to the appearance of the reaction, because when we think about the collision theory, and we'll develop that more with time, if the amount of reactant decreases, then collisions between the reactants are less frequent because there's less of it left. So the reaction should slow down as it approaches the endpoint. And you can think about this kind of like a battery. You know, batteries, as they start out, they have a lot of charge, and they maintain this charge, and then as they go down, as the reactants react, then you can sometimes see this quicker collapse in the voltage that it produces. It's a similar thing here. As you run out of things, the reaction itself also can get slower. Something else. So you can see here that these are not linear. These have some curvature to them, right? And really to make true measurements of this as we go through, we would need calculus, but we don't really need that for our understanding. We can just look at it as a change in some time unit, like 100 seconds over something, and then we can measure the difference between 3 and 400 and get an average rate. Average rates are really, really useful because they often come from a data set where I only collected points with time, so I don't have a full equation that describes it anyway. So an average rate can be very useful in and of itself, and they're using like the hypotenuse of a triangle to estimate what that is. Again, this is graphical and you won't need to do this, but just understand this is sort of what we're doing. We can imagine that the real trajectory of the reaction can be modeled by some curved line like this, and then we're going to measure some time interval across it, and then that's going to give us some sense of like, okay, what was the rate during that time approximately. So we can also measure rates of decomposition, not just like the rate of production of something, and those rates are negative because something's going down, but we conventionally make them positive for chemical reaction rates. That's just something to notice. Be aware of the fact that, yes, we understand that something as it goes down, mathematically it's going to have a negative rate, but we don't ever do that by convention in this field of chemical kinetics. So make sure that when you get negative answers, you think about them and write them as a rate of decomposition being a positive number. Okay, so also what I want to show here is that the rates are related, right? So if we have some rate of decomposition or formation of something, then the other rates relating to the other reactants and products are related stoichiometrically to the rate we base this on. So if we base this on, say, the rate of formation of O2, which has a 1 coefficient here in the balanced equation, then if we want to find the rate of formation of something else, well, then it's because this would be faster, right? For every one of these, we get 4 of these. So this rate is 1/4 the rate of the NO2. So that's why I've got these circled. This 4 is the same as this 4. This 2 is the same as this 2 down here in the fraction. So you can see they are related stoichiometrically. This is formed, and its formation rate is 1/4 the speed of this one's formation rate and 1/2 the speed of this one's decomposition rate. Because the higher these coefficients are, that is related to how fast they are or how slow they are relative to the other reactants in the system, because they all have to get produced and consumed at once. So we can also think of a rate of the whole reaction, which would have a coefficient of 1 and be the same as a reactant or product whose coefficient is 1. And we could think about that as the whole reaction turning over. But a lot of times they'll formulate that in terms of a particular reactant or product, so we got to think about that and remember these conversions. There will be questions on the exam that require you to do these kinds of conversions between different rates. And just remember, these are connected stoichiometrically, just like they would be for like a mole conversion. Rates of chemical processes are connected this way. So that's what they say. We got a general reaction. That's what we were talking about here. We could get a general rate, which is the same as the rate of the formation or decomposition of something with a coefficient of 1. So also we could get an instantaneous rate, right? But to do that, that's really where we got to bring in our calculus, right? If we could shrink the time interval, we get closer and closer to an instantaneous point on a line. Again, if you've taken a calculus class, you'll understand more about this. The tangent to a line, we're not going to be concerning ourselves too much with this, but just understand that it does exist. We can do that as well if we have especially if we have an equation that models the decomposition or production very, very well. So here we're looking at relative rates again and conversion between them, right? So they have this conversion of ethanol into, glucose into ethanol and CO2. And they say, how is the rate of formation of ethanol related to the rate of consumption? Okay, so according to the balanced equation, right, we've got 2 moles of ethanol produced for every 1 mole of glucose. So the rate of formation of ethanol is twice as fast as the rate of consumption of glucose. That's key to that connection to the mole ratio, right? And then to write this relationship, they make this be negative because 1 is a rate of consumption, and that's going to be necessary from a mathematical standpoint. But again, understand that when we typically write these, we write it as a decomposition rate, and then we write it as a positive number. Okay, so the rate law is that equation that gives us that description of the rate as an actual true mathematical equation. Okay, and that's the rate law. So the way we model a rate law is we say that there's some constant, and we'll call it little k. We'll call it the little lowercase k. And that's some proportionality constant that takes care of any other particularities of this specific reaction that don't have to do with concentrations of the reactant. So we're looking at the reaction going forward, right? We're looking at it going forward. So we're not concerned about anything to do with the products. We're just looking at it going forward. So we're saying we have to look at the concentration of the reactants and how many times that concentration matters. How important, in a sense, is that? And we represent that with these m and n variables, how sensitive the rate is to the concentrations of A and B. And these are typically whole number powers. They're typically 1 or 2 or 3 or something like that. They can also be 0, which just represents that they aren't important at all. They don't do anything. Fractional powers are possible for more complex systems, but it's not necessary for anything we'll be doing in this course. But just understand, we can use this basic outline to model any reaction in terms of some k, which is something that's constant. It can be any number you need it to be positive. It's going to be it can be bigger than 1, less than 1. It can be all over the place. And then the concentrations. And these are just the concentrations from up here. So if there was a C, we could put a C in here too. It just goes on. And then you add another exponent, and they don't have to be the same. They can be different numbers. They could be the same. But this is the basic formulation for a rate law. So what we show here is how the exponent affects the equation. So if m is 2, then that means that the rate gets quadrupled as A is doubled. And if it's 1, then as A is doubled, then the rate doubles. The rate has the same effect as what happens to this is typically the most common situation. Power of 1 is typically the most common situation in real life and in most chemical reactions. Sometimes you'll see 2. Higher powers than that are less common. 0 does happen too. It is also possible for things to be negative, but another way to understand that, and something when we come back to later on in chapter 13, we'll see how the presence of products could push backward on the reaction, and that's where this kind of comes more into play. So we're not going to really worry about negative right now. We're going to worry more about just the positive side of things. So we can also get what's called a reaction order, and that's just the sum of the exponents. So again, here we have A to the second power, B to the first power. So the overall reaction order is 3. And we say that it is second order in A and first order in B. That's how we describe that. So if you have a question on a homework or something, or a test question asks you, given this rate, what is the reaction's overall order? It's 2 plus 1, it's 3. What is its order in A? It's 2. What is its order in B? It's 1. Okay. So now's where it gets a little more complicated. How do we get these exponents? And how do we know how much a reaction depends on its particular reactants? Well, ultimately it has to be experimental, because how a reaction proceeds is ultimately a physical process that is difficult to determine from first principles. We will learn that there are some ways to get an idea of what it might be based on experimental data, or by looking at a reaction we might be able to guess and get some reasonable guesses in there, but it really has to be verified empirically. That's what they say here. These values must be determined by experiment. They cannot be determined by the stoichiometry of the reaction. There is a relationship with the stoichiometry of the reaction, but it's not just straightforward. So, for example, they give us an example of some reaction, right, where you have a reactant that's 0 order. I mean, how would you know that it's 0 order unless you know that? Now, oftentimes, like in this example where like water is a solvent, for example, because the water is present in such great excess, having more water doesn't do anything. So that can be represented by making it zero order. Again, the rates are modeling something that I really observe. So it's less about the overall theory and more about what empirically is driving the reactions processes, right? So here they give me some examples of reactions and then their rate laws, and you can see that like sometimes the dependency or something doesn't matter. And the reason for that, there sometimes is a reason for that, but sometimes it's not clear what the reason for that is. Sometimes you do sometimes see a correlation, right, where something that has a higher stoichiometric value might also have a higher exponent. Sometimes that happens, but it's definitely not something you can guarantee. This really does need to be verified empirically. As you can see, there's not always a clear connection. Sometimes there is. And we'll learn that when that is the case, when the stoichiometry and the rate law are the same, we can describe that reaction as what's called elementary. We'll see that in several parts ahead in this chapter. So they give us this example. They say, what is the order with respect to each of the reactants? So we've got the two reactants here, and what is their order with respect to this? So they give us some little picture here, some rate of formation. So they say here, find the reaction order. We're going to have to look at some kind of data here. So they look here at table 12 too. So they go back here and they look for the reaction in here and they find the rate law, and that's how they're able to answer it. There's not a way to just look at this and know that it's only first order in BR2. You did to know that this other component doesn't matter. That's something you'd only really be able to verify with experiment. Okay, so how could we determine the rate law experimentally? Well, we can look at the data, and the data can tell us something, right? So if we start with initial amounts and an initial rate of formation, we can look at what happens, to that rate with time, right? We can look at what happens to the rate with time. So these are all experiments with different initial rates. And if we start out with these, we get this rate. Well, we doubled this one over here. Well, what happened over here? That looks like that might have also been doubled. That looks like a doubling. That suggests maybe it's first order in that one. And then down here, okay, I doubled this. Well, that's another doubling. That looks like a doubling. This must be more than a doubling. Then again, I'm not calculating anything. I'm just looking at the numbers, right? This looks like that might be more than a doubling. Maybe that's a power of 2. And then you can see that here. So you can compare these these with each other, and that's how you can determine it. So 3, like I say, looks like it's doubled from 1 here. So that might be first order. But then up here, there's a greater change than that. That's not just a doubling. You could verify that and compare these. So that might be a 2, a quadrupling. That makes a little more sense. So they show us some initial data, and that's how they're able to finally get this rate law here at the end. They just kind of pick 2 experiments and compare the results. That typically is the best way to get the rate law from a problem that you might be given on a test, because you're not going to want to spend time graphing them. The book talks about graphing these in more detail to get a better sense, or comparing every single one and then doing all of this elaborate out. Typically, you can just pick 2 experiments, find one thing that changes between them, and then see what happens to the rate of formation. You can just divide one by the other, okay? And you're looking for things like 2s, 4s, something that can tell you what needs to be done to that reactant. Because if it's just doubled when something is doubled, then that means that's first order. If it's quadrupled when this is doubled, well, then that will mean that it's second order. And that's the most common. Or if nothing happens, then that'll mean it's zero order. Those are typically your choices. You're not really looking for anything else. Fractional powers and such, they exist in real life, but they don't exist in any of these types of problems that are teaching it to you. So you should be able to either see it, observe it by looking at it, or do a quick verification with your calculator and see how these things pan out. And again, if your rate law, gives you this, it's first order. We talked a little bit about this, like the overall reaction orders first, second, third. And the units for K will matter. There will be some questions that'll ask you to come up with the units of K. The units of K need to cancel everything out so that you end up with a rate that is in that's actually in molar per second. That's typically the units of a rate of formation or a rate of decomposition are in molar per second. So molar, so moles per liter per second. So whatever your unit of K is, it needs to cancel everything out so that that ends up being the case. And that's what they're showing you here. They give you some examples of units for K. You could write these down on a flashcard. You could remember these. This is helpful because most reactions will match up into one of these 4 categories. And so then you can just kind of pick which one it makes the most sense. But you can also derive it from first principles by just saying my rate needs to be in molar per second. So whatever K needs to have as units is whatever it is to cancel that out. And that's what they're showing here. So they say be careful not to confuse the rate of a reaction and the rate constant. The rate depends on concentrations, but the rate constant doesn't. It's a constant. So the rate constant is something there that applies some factor to get us the observed reaction rate based on the multiplication of these reactant concentrations. Okay, so here again we're looking at some data, and we see here determining a rate law from initial reactants. Okay, so what is the rate law? So they want us to look at this data and come up with a rate law. So we write a basic rate law here, and then we got to figure out the powers here. And the way we would figure these out is by looking at the changes. Okay, picking 2 and looking at the changes. Does something double? Well, then it's first order. Does something do something different from that? Well, then maybe some other multiplicative process is going on here. And then to find the value of the rate constant, substitute in data. We don't typically have to go that far, but if you need to find the rate constant, you just will pick one of these data sets and solve for the value of K. You can use any one of the 3 experiments. And then to calculate the initial rate, you substitute into the rate law, and that'll help you get the answer to the C question where you plug those in. So again, here we look at the equation and we can see that it's first order in both. We can figure out the factor. Again, we can see that this one's doubled, so that tells us that this one's first order. And then this one has some, multiplied by, a 0.5 kind of factor. So we compare this one to this one and we see that it's also multiplied by a factor of 1.5. So we could verify that. Sometimes they're not always clearly doubled, but most of the time that's what's going on. Then we can plug and chug any particular step from in there and solve that for our value of K. Plug in the initial concentrations. Once we've done the first 2 steps, just do these in order and you'll end up with an answer. Check the units of the rate constant so that things cancel out and make sure that they're what you expect for a second order reaction. And you can see that the initial is about 3 times, half. You can agree that it should be about that. And you can also estimate for the part down there. Okay, so they talk more about a formal approach. This is the stuff that I said you didn't really need to know. I just want to present this as a possibility. You can do these as a system of equations and take logarithms and solve this all out. Again, for any kind of problems you'll see on a test or general homework, you're not going to have to do anything like this. Okay, so let's look at first order reaction. So we need to know these integrated rate laws. Okay, we start with a first order reaction process. And then we can use some calculus that we don't have to delve into here to get this first order reaction process. And these 2 equations here, I've circled this one because this is the general form you're going to want to use. This one is another form that might be helpful. It involves taking this part out of the denominator of a logarithm. And if you remember addition and subtraction rules of logs, again, not necessary for our understanding at this point, but this is the equation you should write down on your flashcard because you may need to know this for later on review. You'll need to know this equation here. Take a moment, make sure you know the integrated rate law for a first order reaction. We'll need it to solve certain problems. And we see that in a first order reaction, this is kind of like the radioactive decay that we covered in a previous chapter. The radioactive decay follows first order kinetics, so it works the same way. First order reaction exhibits exponential decay of the reactant concentration. And if we plot the slope of the natural log of A at time 0 against time, we can get a straight line. This is the linearized version of this equation. We can think about it that way. And that allows us to also demonstrate that a reaction is first order by plotting it and seeing if it's a straight line. That's a thing people really used to do, but it's not necessary for a lot of our understanding. So remember that K is a straight line, and when we do these plots for a first order reaction, the slope will be minus K. And they talk about a graphical process for doing this. Again, not necessary for our understanding. So they ask us to figure out what the concentration will be of H2O2 after 4 hours in this reaction. So we can model this with the integrated rate law. Okay, with the integrated rate law for a first order reaction right here. So we plug in this is at time t. So they say the reaction is first order, the rate constant is this in the initial concentration. So now 0 here, that's the initial concentration. Sometimes they call this concentration at time naught or concentration naught. That's our initial concentration. And then we don't know what this number is, but we know t is 4 hours, okay? And then we just got to make sure that our k is actually in hours. So they come up here and they give me the rate constant, but it's in inverse seconds. It's not in hours. So I can't just put in 4 here. I'm going to have to convert 4 hours into some amount of seconds so that my units cancel out correctly when I put in this k. So that's just something else to make sure we keep in mind. Otherwise, then we could solve it. We'd have time naught, we'd have k, we have the time, and then we just need to solve for this piece up here. And we can do this by taking the antilog by raising to the power of e and undoing it. So they say here, look, we calculate how many seconds it is. We plug that bit in here. We plug in our rate constant that they gave us. And then we put in the concentration, this, and we solve this for the answer. We take e to the negative this power over here, which cancels everything out and gives us a number, okay? And then, now that we have this number, we can multiply it by 0.3 and give us the final answer. So many problems will work something like this. So this is a good model problem to go back to. Make sure that whatever time unit they give you is the correct time unit for your k. You want to check that. That's how we know. Because k has units of inverse seconds, we know we got to convert these hours into seconds. K's time unit can be anything in theory. You can pick any time unit that makes sense. Typically reciprocal seconds is the most common though. So then they solve this for the time. They plug in the other parts that they wanted to solve, and they're able to solve this for a time so that when the concentration reaches this, it'll be at this time. And yet sometimes they'll want you to convert these seconds into hours or minutes. People don't usually think of large numbers of seconds, but check the problem and see what the problem actually asks you for. Don't do extra work unless you need to, right? Don't do extra work. And when they want 90%, if they give you percentages, you can see that they plugged this in here, okay? They just put in whatever that number was, which is 0.3, the initial number, and just said, well, 90% has decomposed, 10% remains. So it'll be 10% at time, and this will be 100% down here. So that's how they're able to correct. Sometimes they'll have these problems where they say, when 90% is decomposed, what do I do? Well, what you'll do is you'll use 10%. That's how much is left, because that's what goes in. The amount at time t is what's left, not what has been consumed. Make sure we're reading the problem very clearly. So then we can again plug in our rate constant, solve the integrated rate law, and get an answer for the time at 90% decomposition. Again, you can do plots that can help you verify this. Again, I find most of the time the plot takes longer than just doing the problem. All right, so that is the end of this particular lecture. If you have any further questions, feel free to reach out to me, and I will have you'll be able to continue this on into the next lecture. Thanks so much, and bye-bye. Oh, I'm done, but I wasn't sure how to stop it with the first one, and then I'll do this.